Hello, everyone, and welcome to the IWCS webinar series. My name is Michelle Malsop. I work for IWCS, and I will be your moderator today. Just a few housekeeping items before we begin. During the presentation, please, if you have questions, put them in the chat function, and we will address them at the end of the webinar as time permits. And today we're going to welcome Michael Dodds, test engineer from Leviton in Pennsylvania, USA. And he will be presenting his paper on the efficacy of noise mitigation strategies against packet cybersecurity attacks. Michael Dodds received his Master of Science in Electrical Engineering and Biomedical Engineering from Drexel University in 2017. He is currently a test engineer at Leviton's New Holland facility. Very impressive. So, Michael, if you would like to begin, I will stop sharing and you can begin.
Sure. Thank you very much, Michelle. Let me go ahead and share my screen now. All right. Can you see that?
Yes. Perfect.
All right. Wonderful. All right. Well, good morning, everybody. My name is Michael Dodds, and today I'm going to be presenting on a topic that's become increasingly prevalent. The more and more various aspects of our lives become reliant on IP-based communications, and that general topic is cybersecurity. And in this paper entitled Efficacy of Noise Mitigation Strategies Against Packet Cybersecurity Attacks, we're going to examine the role that copper cable can play in reducing the success rate of potential hackers. So before we delve into the details of our paper, I'd like to frame the questions that we hope to answer with it. So number one, which cable designs are better at mitigating external noise than other cable designs? So like which construction features will make a cable more conducive to preventing cybersecurity attacks than others? Secondly, which link segment topologies are better at minimizing external noise? So a similar question. So like what length of patch cords, what number of connectors, various considerations like that. What will help you prevent cybersecurity attacks from a link topology construction standpoint? And lastly, which combination of cable and link segments are most susceptible to cybersecurity attacks? So which cable construction, which link segment topology in combination with one another will make you most susceptible to the kind of cybersecurity attack that I'm going to outline in this presentation. So to answer these questions, we'll start off with a brief summary of 10G base T transmission, Cat6a cable design, and a method for using embedded IP packets to infiltrate networks. I'll explain what specific cable designs and link segment topologies we tested. We'll delve into how effective those various cable designs and link segment topologies are at preventing cybersecurity attacks. And that'll be explained through the results of two different experiments that we conducted. One which used a waveform generator in combination with an oscilloscope, and another one that used that same waveform generator in combination with a 10G frame error rate tester. And lastly, I'll delve into which cable and link designs are most effective at mitigating external noise, and subsequently, which cable and link designs are the most resistant to cybersecurity attacks that are demonstrated in our paper. So just to start off with the general information, 10G base T is a 10 gigabit per second Ethernet standard that's been around for over 15 years now. It was first defined in IEEE 802.3 AE. It's very commonly deployed via Cat6a link segments, and it's specified out to 500 megahertz. And unlike, well, relative to gigabit Ethernet, external noise is a bit of a greater concern just because you're covering a wider bandwidth. And alien crosstalk is one of those noise sources, and that's defined as noise generated by adjacent category cables. And because of this, because Cat6a cables are very commonly deployed for 10G base T transmission, Cat6a cables must be designed in order to mitigate alien crosstalk so you can have a successful communications. So there are a number of different ways to design cables in order to resist external noise and alien crosstalk, some of which are more effective than others. And some of the most common constructions are shown on the screen here. So number one there, you basically have a striated jacket where there's no metallic isolation element whatsoever. It's basically just using air as an insulator to insulate the individual pairs from external noise. Number two there, you can have a discontinuous metallic isolation wrap. So it's not a full shield, it's metallic elements that are discontinuous throughout the length of the cable. So there's no need for any kind of grounding or bonding, but it provides you that metallic element to isolate the core from external noise. Number three there is a continuous metallic isolation wrap enclosed between non-conductive materials. And then the last one there, number four, you just have your traditional FTP, so an overall metallic wrap with a ground wire. So naturally, the components that are used within Cat6a channels need to mitigate alien crosstalk as well. So you'll see a lot of the design features common to Cat6a cables being utilized on connectivity and patch cords as well. So you'll see metallic elements on plugs, Cat6a plugs. You'll see metallic elements on Cat6a jacks as well. And you'll also see shielded patch cords with shielded plugs using like similar design features that you'd find in Cat6a cables or in horizontal cables. So Category 6A cables are evaluated for alien crosstalk resistance specifically within the standards, but the thing is alien crosstalk isn't the only source of external noise out there. And the consequences of not mitigating properly for all forms of external noise is you could yield errors in your network communications, but in some scenarios, these errors could actually form cybersecurity risk. So one form of packet-in-packet cybersecurity attack that I'm going to outline in this presentation relies on errors being induced on insufficiently protected Category 6A channels. Basically, what they rely on is faulty link segments for errors to be induced via either changes in environmental factors like temperature or externally induced noise. And using those errors, they can formulate a successful cybersecurity attack on your network. And I'll delve a little bit more into the details on the next few slides here. So I know a lot of us concentrate primarily on the passive elements of cable performance. So I'm going to give a very brief summary of datagrams in the sense of IP-based communications, because that's really the crux of how this type of attack is successful. So in an IP packet, you basically have four main elements to it. You have the preamble, which is signaling to the Ethernet port that information is coming, prepare to read it. You have headers that specify what type of information it is, where it's coming from, where it should be going. Then you have the payload, which is the actual useful information that's being sent via the packet. So if you're downloading a file from the internet, the payload would be basically chunks of that individual file that you're trying to download from the internet. And then the checksum is just to verify that all the contents of the packet were transmitted successfully. Like there weren't any errors within the payload of the packet that could cause loss of data or improperly obtained data. So in general, firewalls can block datagrams with unauthorized headers. So if they detect a packet coming from a location not authorized by the firewall, they can just chuck it out. Or if it's a type of data that shouldn't be coming through the firewall subsequently can throw it out. But what you can actually do is you can embed a second packet within the payload of an external packet. So effectively, the payload of an external packet that could be masked to look like a completely benign packet within your network could have a payload that has elements of another packet. So effectively, you can use this embedded one to issue commands being disguised as maybe a benign packet that would be authorized within your network. In order for this kind of attack to be successful, though, attackers do need physical access to your network, and they need to know specific information about it. So MAC addresses, authorized IP headers, and information like that. But with adequate information, they can successfully embed malicious packets within benign external packets that can traverse your network security measures. So I'm going to use three different scenarios here to kind of better describe how this kind of attack works. So in scenario number one here, you have an attacker basically just sending a malicious packet to a victim's PC trying to traverse a firewall. But because it's not being masked by any kind of external benign packet, the firewall detects that it's not authorized information, blocks it, throws it out, nothing happens to the victim PC. In a second scenario, you have someone trying to embed a malicious packet within an external benign packet. In this scenario, it has headers authorized by the firewall. It can traverse it. But when it gets to the victim PC, basically the victim PC only sees the internal packet as kind of nonsense. Like, it doesn't know what to do with it because the payload isn't the structure of anything that they would expect in the form of a command. So it basically just, the PC ends up throwing it out and nothing happens to it. But in a third scenario where the attacker is successful, you have the same thing where a malicious packet is embedded within an external benign packet. An error gets induced on that packet, which causes that external benign packet effectively to be shedded away. And if you want more details about how this actually happens from a more detailed standpoint, I encourage you to read our paper about this, because I go a little bit more into detail of how this works in that. But the long story short is that external noise is induced on the packet. The external one is shedded away, and you end up with a malicious packet that has traversed your firewall and can now issue commands to your PC. So there are a number of different things that this packet could be used to do to your PC. One of the most common ones would be effectively the packet telling your PC to use a different domain name server to navigate on the internet. So when you type in google.com in your browser, basically you go to a authorized domain name server. It tells you which IP address to get to google.com, and you go to it. So there's kind of a level of trust there. But with a malicious packet, effectively the attacker could give you a completely invalid IP address. You type in google.com on your browser expecting to be taken there, but you could end up being taken somewhere completely different, unbeknownst to you. So that's just one example of the kind of attacks that could be implemented through this form. So now onto our test setup. Now that we understand the basics of Cat6a, 10G-based transmission, and packet attacks, we're going to talk about how we answered the 3 questions of our paper. Question 1 and question 2 were addressed in the first experiment that we conducted. So basically what we did was we took 4 different types of Cat6a cables, and these were the cable constructions that I mentioned in the introduction. And we used 4 different link segment topologies and tested them for each of the Cat6a cables. So we had 16 different combinations of Cat6a cables being mixed with different topology constructions. And before any of the tests that we performed, we validated that these Cat6a cables and link segment topologies were in compliance with the Cat6a spec, the TIA one. So each cable topology combination under test contained a disturbed region. And in this disturbed region, we had matched pairs that were extracted from a separate sample of the cable under test. And they were affixed to the outside of the channel using a non-metallic binding. What this did was it brought the disturber pairs closer to the victim pair relative to a standard alien crosstalk test. So like in a standard alien crosstalk test, you might have 2 adjacent cables next to each other inducing noise on one another. But what we did is we took the cables out of that disturbing cable and affixed them to the outside of a victim one. So it closed down the distance between the disturbing pairs and the victim pairs and increased the rate at which noise is being induced on that victim cable. And the noise that was being induced on those disturber pairs was generated by a waveform generator with a frequency range between 1 and 500 megahertz with an amplitude of 2 volts peak to peak. And then just to better illustrate what I was mentioning about the disturber pairs. So for example, if you had cable 1, the disturber pairs came from a separate sample of cable 1 and were affixed to the outside of the victim cable. So the 4 link segment topologies that we evaluated in our study are shown below. So in number 1 there, you have a 100 meter 2 connector channel with a 5 meter shielded patch cord within the disturbed region. And in scenario number 2 there, you have a 5 meter equipment cord. So an equipment cord would basically be a patch cord, but the cable component of the patch cord is constructed from the same cable as the horizontal. And in scenario number 3, there's a 1 meter shielded patch cord. And in scenario number 4, there's no patch cord or equipment cord. It's basically just a direct attach from the horizontal cable to the port that it was connecting to. And in all the scenarios, there was a 5-meter shielded patch cord at the far end of the channel. And the disturbed region in each of these different topologies consisted of the patch or equipment cord, if there was one, and 15 meters of the cable under test. And one thing to point out here is that the coupling between the cable and the disturbers was greater than the coupling between the patch cords and the disturbers, because the disturbing pairs weren't matched to the patch cords. They were matched to the horizontal. So there's a greater degree of coupling between them. And in all the scenarios where FUTP cable was used, we used shielded jacks. And for all the scenarios where UTP cables were used, we used unshielded jacks. So the physical setup of the passive test was as follows. At the near end of the cable topology combination under test, we connected it to an oscilloscope. And at the far end of the cable topology combination under test, it was connected to a resistive termination network standard to TIA. The near end of the disturber pairs were connected to a waveform generator that induced 2 volts peak to peak Gaussian white noise, 1 to 500 megahertz on the disturbing pairs. And at the far end of the disturber pairs, they were connected to a resistive termination board. And with the waveform generator active, the peak-to-peak voltage was measured on each of the 4 pairs in the cable topology combination under test. So we were measuring how much noise was being transmitted down each disturber pair and how much was being picked up on each of the pairs within the cable topology under test. So now on to the third question of our study, and that's which cable and link segment topologies are most susceptible to the packet-to-packet cybersecurity attack I described earlier in my presentation. So to answer this question, we use a very similar setup to the one in the voltage transfer test I described two slides ago. The near end of the link segments used in the previous test were disconnected from the oscilloscope and connected to one port of a 10G frame error rate tester. Likewise, the far end of the link segments used in the previous test were disconnected from their resistive termination module and connected to a second port on a 10G frame error tester. So we could measure the data being transmitted bidirectionally over the Cat6a cable topology under test. And over the span of 1 hour, we transmitted 194 byte frames bidirectionally over 10G base T. And within the payload of those 194 byte frames, there was a embedded 140 byte frame. So it matches the form of the embedded packet-to-packet style attack that I described earlier in the presentation. And while these frames were being transmitted, we induced noise on the disturber pair, similar to how we did in the voltage transfer test described 2 slides ago. So now onto the results. We'll start with the voltage transfer experiment. As a reminder, this was the test in which we affixed disturber pairs to the outside of link segments under test, applied Gaussian white noise across the entirety of the 10G base T frequency range. In scenarios where we used a 5-meter shielded patch cord across all of the cable designs under test, there wasn't any voltage transfer observed. There was a greater voltage transfer observed with the 1-meter shielded patch cords than with the 5-meter shielded patch cords. So effectively, the amount of noise being picked up at the end of the cable topology under test was reduced by using a longer patch cord versus using a shorter shielded patch cord. And the greatest amount of voltage transfer was observed with the UTP cable across all the various topologies that we tested. There was some voltage transfer observed with the discontinuous wrap, but it wasn't to the magnitude that we saw with the truly unshielded UTP cable. So the one without any metallic element had the greatest amount of noise. The one with a discontinuous metallic element had some noise, but not to the same magnitude as the one without any metallic isolating element. And there wasn't any observable voltage transfer in either of the cables that had the continuous isolation wrap or the one that was a fully shielded FUTP cable. In terms of active performance, we saw similar trends relative to the passive testing. There weren't any errors observed when the cables under test were connected to a 5-meter shielded patch cord, which makes sense. We didn't see any noise being induced in the voltage transfer test in those topologies either. But there were more errors observed when we used a 1 meter shielded patch cord relative to a 5 meter shielded patch cord. And in all of the topologies except for the 5 meter shielded patch cord, the greatest number of drop frames were observed with the fully unshielded cable without any kind of metallic isolation wrap, and it was several degrees of magnitude more than any of the other cable designs that were under test. There were some drop frames observed with the discontinuous isolation wrap when using the 1 meter shielded patch cord or the direct attach RJ45 plug configuration. There were only 3 errors observed when using a direct attach RJ45 plug with the continuous isolation wrap cable, and there were no drop frames observed for the fully shielded cable in any topology. Similar to the number of drop frames, there were clear trends that tied back to the results of the voltage transfer tests that we conducted. So one way to understand the results on on this slide here is effectively the number of successful packet-in-packet attacks is effectively a subset of the number of drop frames. So a drop frame could result, an error being induced during the active portion of the test could result in simply a drop frame. But if that error occurs in a very specific spot of the packet being transferred, then it will result in a successful packet-in-packet attack. And like I said before, if you want to know more specifically how this kind of attack works, I encourage you to read our paper. But in general, the numbers that you see here are effectively a subset of the number of frame errors being induced on the cable topologies under test. So there were 0 successful packet-in-packet attacks when the cables were connected to a 5 meter shielded patch cord, which makes sense. There weren't any induced frame errors in those scenarios, so there weren't any successful packet-in-packet attacks. There were more successful packet-in-packet attacks against topologies that use the 1 meter shielded patch cord than the ones that use the 5 meter shielded patch cord. And the greatest number of successful packet-in-packet attacks were observed with the fully unshielded, no metallic isolation element whatsoever, UTP cable. And there was 1 successful packet-in-packet attack observed with the RJ45 plug direct attach topology with the discontinuous wrap. And even though there were drop frames with some of the continuous wrap scenarios, there weren't enough drop frames such that the probability was high enough for packet-in-packet attacks to be successful over the span of 1 hour. So having errors doesn't necessarily mean you're going to have a successful packet-in-packet attack. It just increases the likelihood that you're going to have a successful attack over a fixed time period if you have more errors. And that's kind of an important trend that I want to point out with this graph right here. So on the y-axis, you have the number of successful packet-in-packet attacks, and on the x-axis, you have the total number of drop frames over the span of 1 hour. So there's a pretty strong direct correlation between the two of them. So the main takeaway there is the greater number of drop frames over a fixed period of time, the greater number or the greater likelihood that there's going to be a successful packet-in-packet attack over that same period of time. So now to our conclusions. Based on the results of our testing, we can draw a number of different conclusions. So first, both cable construction and topology affect the link segment's overall resistance to external noise. Topology-wise, longer shielded patch cords appear to do a better job of mitigating external noise than shorter shielded patch cords. In terms of construction, fully shielded cables and cables with continuous isolation wraps appear to be the most resistant to external noise, followed closely by cables with discontinuous wraps. And then the least effective that we saw were the fully unshielded cables without any kind of metallic element to isolate them from external noise. So what this means from a cybersecurity standpoint is that fully unshielded cables and cables with continuous isolation wraps may generally be better at mitigating external noise, which in turn makes them more resistant to mitigating successful packet-in-packet attacks. So the way to kind of understand this in a general sense is that ultimately the goal is to maintain an adequate signal to noise ratio, and by doing so, you're going to better protect your network from successful attacks. So it's kind of a balancing act. You need to maintain signal strength while also preventing noise from being induced on your channel. And by using intelligent link designs and properly chosen cables, you can better protect your network from this kind of attack being successful. And with that, I will open it up to some Q&A.
Thank you, Michael, for that wonderful presentation. So it looks like we have one question from the chat, which is, what was the gap size of the discontinuous shielded tape?
It was minimal. It wasn't a, I can't give you a direct answer off the cuff, but it was a very small gap between the metallic elements of the cable. So it wasn't like there was like a full inch gap between the metallic elements of the discontinuous tape. But it was small. It was typical of what you would see in usual cables that use that kind of design.
Okay. It looks like we have another question coming in. So I will just say that all of these presentations in our webinar series are recorded and will be on our website in our archives. Our next webinar will also be Friday, January 20th at 10:30 a.m. Eastern USA time. And you can continue to put in your questions. We still have a few more minutes. So Michael, Paul Watchell just asked, did you investigate different lengths of coupling besides 20 meters?
We used, there were different lengths that were used for the various topologies, and it depended upon the length of the patch cord or the equipment cord that we were using. So in two scenarios where there was 20 meters of coupling, 20 meters of disturber pairs that were used to couple noise onto the link topology under test. So effectively, we looked at 20 meters, 16 meters, and 15 meters, and that was effectively the 15 meters of the horizontal cable under test with whatever the patch cord or equipment cord was. So we only looked at one fixed length of disturber pairs per topology that we tested. So we didn't look at at any additional lengths for each of the topologies, if that's what your question was. And part of the issue was effectively extracting the pairs and getting a uniform fixture around a cable link topology under test is a bit tricky. It's something that we were learning to do as we were doing this experiment, but it is something I think would be worth looking into in a future experiment.
Okay. Before we conclude, I just want to check to make sure that there are no last minute questions from anybody. Oh, and we do have one. Did you try the same test with disturber pairs still being in a cable and not removed?
So if I understand your question correctly, you're asking if we did the same kind of, if we induced noise on the disturber pairs within a second external cable, just as you would with like a normal alien crosstalk test. We didn't, but I would expect the results from that experiment to be the amount of noise to be lesser, the amount of induced noise to be lesser, just because you're increasing the distance and you're increasing the distance between the disturber pairs and the victim pairs of the horizontal cable under test. So we didn't do that experiment, but I would expect the noise to be lesser. Because what we were trying to do was we were trying to make a noise induction that goes beyond the typical noise induction test that you would do for like a compliant Cat6a channel. Is we wanted to make it as worst case as possible. So that's why we wanted to fix it to the outside of the cable to make the distance between disturber and victim pairs as little as we could.
It looks like Anthony might have been, oh, not a question. He just wants to thank you for sharing your work.
Yep, no problem.
Does anybody else have any questions they would like to submit? All right, then. Well, We want to thank Michael very much for his presentation. We also want to acknowledge our sponsors for this. We could not do these series without all of our sponsors, and remind everybody of our upcoming Cable and Connectivity Forum for 2023 in Orlando. So thank you all for attending, and we will see you next month.